All right, today we're going full-on cosmic detective. We're diving deep into one of the craziest, most extreme places in the entire universe, a globular cluster called M28.
So picture this, M28. It's not just a bunch of stars. It's more like a super ancient, super crowded city of stars. I mean, it is packed so tight that the stars are practically on top of each other. And in a place like this, stellar corpses, long dead stars, they don't exactly get to rest in peace. No, here they get a second life. And that's where things start to get really weird.
And this is really the heart of the mystery, the big question. We're seeing stars that are way older than our own sun. They should be old, slow, basically retired. But instead, they're spinning hundreds of times a second. I mean, faster than a kitchen blender. How on earth is that possible? Well, to solve this puzzle, we have to take a look inside what you might call a cosmic recycling factory.
Yeah, that's right. The main idea here sounds like something straight out of sci-fi. It seems that in these incredibly dense clusters, nature itself has built a factory, one that takes old, dead stars and spins them back up to unbelievable speeds.
Okay, so the specific objects we're hunting for are called millisecond pulsars, or MSPs for short. Now, what are they? Well, they're basically ancient neutron stars. Those super dense cores that get left behind when a giant star explodes in a supernova. By all rights, they should be slowing down, losing their spin over billions of years. But something is doing the exact opposite. It's spinning them up again. So how does this whole recycling thing actually work? It's basically a three-step process. First, you've got our super dense neutron star orbiting really close to a normal living star. Then, step 2, the neutron star's gravity is so intense it starts yanking material right off its companion. It's literally stealing it. And third, that stream of stolen gas and dust acts like someone giving a constant push to a merry-go-round. Push after push after push, and pretty soon, that dead star is spinning at these insane speeds. Now, this whole process can get pretty extreme, and in the most extreme cases, we find these systems that scientists have nicknamed spiders. And the name fits, because these pulsars are literally eating their companions. It's this brutal, cannibalistic dance, and honestly, they're some of the most fascinating things to study in the cosmos.
And yeah, astronomers really leaned into the creepy theme with the names. On one hand, you've got black widows. These are the ones consuming really tiny, lightweight companion stars. But then you've got the redbacks. They go after larger companions, and that whole messy process makes them glow way brighter in X-rays. And for our detective story, it's one of these redbacks that's our main suspect.
Okay, so our detectives had their suspect profile. It's a redback spider pulsar. So they pointed their telescopes right into the heart of that chaotic star city. And they weren't just looking for any redback, they were zooming in on one specific target, a source they call M28I, to see if they could get it to talk, to spill its secrets.
So, how you interrogate a star? Well, you don't just look at it, you listen to its heartbeat in X-rays. And when they did that for M28I, they found some amazing new clues hidden in its light.
This right here, this is the key piece of evidence. It's a graph that shows us the pulsar's brightness in X-rays over one full 11-hour orbit. And you can see right away, the brightness isn't steady at all. It goes up, it goes down in this really distinct repeating pattern. It's almost like we're watching its cosmic heartbeat, and that gives us a perfect window into what's really going on.
And when the scientists looked closer at that pattern, they found it, the smoking gun. You see, the graph doesn't just have one peak during each orbit. It has two distinct peaks. And that's not just random static. That's a message, a clue, telling us something very specific is happening.
So what could cause a double beat like that? Well, the analysis points to something pretty violent. See, the pulsar is shooting out this powerful wind of particles all the time. And when that wind slams into the stuff being stolen from its companion star, bam! It creates this huge glowing shockwave. And that double peak, it's telling us that the shockwave is actually wrapped around the pulsar itself, and we see it flare up twice every orbit as it spins into our view.
But decoding that X-ray heartbeat was just one piece of the puzzle. This investigation also went after another, really fundamental mystery. Just how big is a neutron star? I mean, what's its actual physical size?
And you might think that's easy to figure out, but it's actually a massive challenge. As the paper points out, the single biggest problem is that we just don't know what the star's thin outer atmosphere is made of. It's what scientists call a systematic uncertainty. It has nothing to do with how good their telescopes are. It's a fundamental blank spot in our knowledge that messes with all the calculations.
This here shows you the problem in a nutshell. Look, if you run your calculations assuming the atmosphere is pure hydrogen, you get one answer for how big the star is. But if you assume it's made of helium instead, you get a totally different answer. So the result completely depends on an assumption you have to make right at the start.
But even with that uncertainty, the team was able to narrow things down. If they assume a hydrogen atmosphere and a pretty standard mass for a neutron star, they calculated its radius as somewhere between 9.2 and 11.5 kilometers. Just stop and think about that for a second. We're talking about an object the size of a small city that has more mass packed into it than our entire sun. The density is it's almost impossible to wrap your head around.
So, after all this incredible detective work, what's the final verdict? Why should we care about these clues from a star system so incredibly far away?
Okay, let's break down the big discoveries. First, and this is a huge deal, they mapped out the shape of that shockwave in a redback system for the very first time. Second, they gave us a much better, tighter estimate for the size of a neutron star. And, just as a little bonus, they found 6 new flickering X-ray sources in M28. So this pulsar paradise just got even more mysterious.
But here's the real kicker, the ultimate why this matters. Measurements this precise are a direct test of what physicists call the equation of state. What's that? You can think of it like the ultimate rulebook for matter, the fundamental physics that says how stuff behaves under the most extreme conditions in the entire universe. By measuring these pulsars, we're literally checking to see if our fundamental understanding of physics is correct. This is pushing science to its absolute edge.
And that really leaves us with one last big thought. When we study these tiny, impossibly dense objects spinning at blender speeds in a star city that's billions of years old, we're not just looking at stars. We are testing the very fabric of reality itself. And it just makes you wonder, by getting these impossibly precise measurements, what fundamental laws of the universe are we going to rewrite next?